Hello, I'm Neil,
And I'm Daniel.
and this is our Hyperloop prototype for ME190. As you can see, our Hyperloop prototype uses an LN298 driver board connected to our Arduino, and it uses a temperature sensor called LM35 to measure the heat given off by the driver board. So we have two motors on this robot, and these motors will generate the heat for the driver board. What's important to note is that we chose this driver board because it has an open heatsink, so it was easy to apply the temperature sensor, and we connected the driver board using the IN1, IN2, IN3, and IN4 inputs, and we connected that to our Arduino using inputs 5, 6, 10, and 11. And one thing is that the important thing is that you need to have the ground wire connected to your Arduino ground, otherwise the circuit will not be complete. And our temperature sensor is connected to the power and ground on the Arduino, and it uses analog input 1.
So in order to operate the motor at various voltages, the pins need to be hooked up to the Arduino pins that can do PMW signals. So in this case, the Arduino can do that on pins 3, 5, 6, 9, 10, and 11. For our project, we chose 5, 6, and 10, and 11. Here is our code that we used. So we have our pins for the driver motor, which are hooked up to the PWM, which are hooked up to the PWM pins. We have our temperature sensors going to be hooked up to analog 1 in our case. It can be changed to any of them. We have a couple of terms that are going to be used in our functions that we're going to call, which we'll show later. Here's our setup. We set up our control to have a KP value of 4, KI value of 1, a KD value of 0. We found this to be the best in our case to get a response, but these values can be changed and tinkered with testing. The output limits of our motor PWM signal goes from 0 to 255. So in this case, that would mean it would go from 0 to 9 volts as the maximum. If our thing tries to calculate anything higher, it'll go directly back down to 9 volts, and if it tries to calculate anything lower than 0, it'll go back up. We're sampling every half a second and changing the output. So we've set all the pin modes for the motor driver to be an output. In our case, we have set pins the IN2 and IN4 to always be low. We're going to just run the motors for the wheels to always be in a forward direction. In subsequent coding, in subsequent projects, these can be changed along with the other two to allow the RC car to move forward, backwards, and turn. So we read the temperature value in, we convert it to both Celsius and Fahrenheit. We put that as an input, and then we compute. We will call the compute function, which I'll show a little later, which will then give us a new output, which we will use. So we change our output of the PWMs to be anywhere between 0 and 255, which again is equivalent to either 0 to 9 volts, between 0 and 9 volts. And we also will print out the time, the temperature in Fahrenheit, and the output in volts, which this is the conversion right here to do that. Here's the compute function. It takes in the amount of time that's passed before the last time it's computed, calculates the amount of error between the temperature we want and the temperature It's reading, multiplies it by that error by the KI values, the KP values. It also takes the difference in the input of of the last calculation and the new calculation and subtracts that value, but we don't have any KD values in our case, so that just drops out. And it gives us a new output and stores the values for later computing, which we used. Here's the code for how to tune the controller, how to change the sample time, and how to set the output limits, all of which were called in the setup. So in our case, this can be run and just monitored via the serial on the Arduino's IDE, but we instead have created a little MATLAB function which will allow us to store the data and graph it. But we're just going to run the serial monitor for this video.
Yeah, this MATLAB logging was created through our homework assignment that allowed us to gather data from serial monitor that was outputted by the PSOC. So it's based off of the UART bridge.
So now I'm going to hook up the Arduino.
And we will demonstrate the operation of the robot with its controller.
All right, so we've set the power source to 9 volts, and so we'll reset the Arduino once it's set to 9 volts. Yeah. We'll reset the Arduino's calculation. So it's I'm downloading the program at the moment, but we've hooked up the power source now. Oops.
You can tell it's a prototype because we haven't really bolted anything down. So this allows us a lot of customization.
But now we see data coming in. The voltage is rising steadily, and we're reading in. On the left is the amount of times in seconds that has passed. In the middle is our temperature in Fahrenheit, and on the right is the voltage. And you can see and hear that the wheels are spinning faster and faster as it is trying to raise the temperature of the driver board.
We've also tried to calculate an optimal controller using the MATLAB PID tuning, but we will show in the data in our report that the PID tuning did not give us a controller that would work in our time scale.
Yeah, the temperature and voltage levels rise at an extremely slow pace. So we want the vehicle to actually be able to run before it stops to cool off. We weren't getting that. It would take a long time for it to get to the temperature we want. So as you can see, the has reached its maximum voltage. It can't go any higher, and the temperature is increasing.
So now we're reaching our cutoff temperature.
Yep. So the vehicle should now soon start to respond to the fact that we've reached our target temperature. Since it's so close, it will maintain its voltage, but it will eventually start rising above the temperature. because the temperature has now increased, the voltage is beginning to try to drop. And now it is steadily slowing down as it has noticed that the temperature is now above our desired cutoff. Now, even though the voltage is decreasing, the temperature does continue to increase. This is because the response of the driver board is extremely slow. It takes over 3 minutes for it to heat up properly, and it takes even longer for it to cool down. So we would most likely need to include a fan to our design in subsequent models.
Or we can try to take off the heat sink so we can have a faster response.
Yeah, that's how this operates.
This will heat up to about 80 degrees. It will then cool down. Once it starts to cool below 75 degrees, it would speed up. But it would take too long for this video.
So that completes our demonstration. So that completes our demonstration. And now we will end this video. So this has been a presentation by Neil.
And Daniel. I really hope my face is right.
Alright, can you stop the video now?